Hello everyone. Hello Emilio and Patricia. Today I would like introduce to yours the idea that in physics we use a lot of the Schrödinger equation. Schrödinger equation. I won't derive just the derivation. There are many ways to derive this equation. One of them is given by assume some particles which has behavior or a wave like the Broglie wave, and they satisfy one differential equation that is given by this equation. But now my purpose is just introduce the idea of quantum mechanics. So to do that, to introduce quantum mechanics for yours, let's start giving the comparison between the macroscopic scale. Let me write it. Okay, with a color, let me select okay, this with macroscopic scale. Macroscopic scale. The macroscopic scale is usually is when it's not microscopic, but is near to meters. Okay, it's proportional to meters usually. For example, when you have a guy, let's say write this guy. This is me. I need a smile. Okay. This is me. So okay. Usually the macroscopic scale is given by behaviors of the nature near to meters. In this case, the distance of my is 1.77 meters. This is the altitude from the ground state to my head, top of my head. Okay. When we have some physical process which are close to meters, we call that a macroscopic effect. However, when we see the mountains, here we have a mountain, and here, I don't know, okay, here we have a sun. No, this is not a, okay. Okay, this is our nature. Okay, here we have a river. And blah blah blah. and some days here. Okay. Okay, and here one house. Ding, ding, ding. Okay, so when we see a landscape in our nature, this scale is close to meters. Okay. However, there is something interesting that happens in the nature that I want to understand, and I am spending many years to connect this with something more interesting. Or also is interesting. That is given by this. This is the bar of the scales. Let me write something like this. Okay. Okay. So when the bar is this distance, let's call a meter. Okay, 1 meter. But this is something more reduced, and so on. We can reduce and reduce and reduce until very, 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 very small distance between 2 points from here to here, from here to here. When this, okay, this, let's call this distance 1, or distance of microscope, it's 1 meter. But when we have one distance, or the distance between 2 points is close to, or is near to, let's think 10 minus 9 meters. That is 0.09 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 0. We can count if I did a mistake. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, he's one less. It's here. Just we count the zeros. This is the conventional method that we use to. Okay, 1 here, 1, 2, 3, 4, 5, 6, 7, 8. I was okay. Sorry. People will say, what are you doing? What, you don't know how to do that? Okay, never mind. We have many zeros, okay? So, when we reduce the distance between 2 points in our space, occurs something interesting. The microscopic scale becomes a quantum scale. We will have quantum scale. It's not clear. Would write better. Scale. Okay, so this is the quantum scale, and now there appears something like new properties of the nature, or is more you can see some interesting effects of the quantum scale. This is the particles has a behavior of a wave. This is very trivial to explain, or is trivial the phenomena, but to explain now. If you have here a generator or I mean not generator, but how we say, this is a okay, this is a an emitter of electrons. That is the name of this device is tube of cathodic rays, but in other words, via differential of potential should be emit electrons. Here we generate electrons on this direction. When we do that, some electrons will pass from here, another kind of electrons will pass to here, but those, if we count the number of electrons, we will see something interesting.